Hello everyone. This is gonna be a second video, which is in this video we try to define functions using uh, several notations that we use, and how we can differentiate a function from other four types of mapping. So as I said earlier in the previous video, there'll be four different types of mapping that uh, we can see in general relationships, general types of mappings. Out of the four, there'll be some types, right? So there'll be actually two types of mapping that can be called as functions. So in A level, advanced level, combined mathematics classes, and from here onwards, when you define functions, you have to know certain things. So you cannot define everything as functions, and we are focusing only on algebraic functions in this case, and we are only focusing on real numbers, right? So keep this in mind. We are only focusing on real numbers, the set of real numbers, right? All the rational, irrational, integers, right? Positive, negative, everything, all the real numbers. We are not considering about complex numbers or imaginary numbers. What are imaginary numbers? Square root of -1, that this is an imaginary number, so we denote this as simple line. So you may not have heard of this before. We will learn this in the future, but not anytime sooner. Okay, so very well about real numbers, set of real numbers. So we are only basing these definitions on the real numbers only for the moment. Okay, a function, how do you define a functions? As we talked about in the first slide of the previous video, functions, what does a function do? Like every other mapping, there will be an input. So input goes through some sort of an operation. So in these operations, the operations are defined by the functions. So different functions have different operations. So this will put out an output, right? There will be an output. So what is an operation? Let's say cooking is the operation here. Sorry about this. Cooking is the operation. So cooking, in cooking you can have different set of inputs. Let's say you're going to cook a pizza. So what do you need? You need flour and what do you need? Yeast, water, and you need an oven and things for those toppings, right? So when you input those ingredients into this, and then you're gonna have to uh, adapt to a certain operations that are necessary to cook a pizza, right? Different set of operations, which is called the recipe, right? So the recipe should be followed through. If the recipe is followed through, you will get an output, which is the pizza, right? Pizza. So if you don't get a pizza, something has happened there. So can there be two types? So if you put these ingredients according to the recipe without changing a bit, can there be a pizza as well as, let's say, fried rice? No, right? You can only have one output, just one output here. Okay, so keep that in mind. A function is a correspondence that associate with each and every element x of a set x to one and only one element y of a set y. So this is a long sentence here. I will tell you the meaning of this in few seconds. Right, what does this mean is that each and every element, remember this, each and every element, no element is left behind. each and every element. So in other case, all the elements in X, all the elements in set X. What is the set X? We usually define set X as the domain. So each and every element of set X to one and only one element Y of set Y. Right? Set Y here is the codomain. So there should be let's say you have a codomain here and this is the domain. So you have objects here, sorry about this, objects here. So you can have this, right? All the elements should be mapped. It's quite difficult to draw it here, so we'll draw it somewhere else. So the basic thing you should remember is that all the elements in the domain should be mapped to at least, not at least one, sorry, only one element of the set Y. So this does not mean that all the elements in the set Y, all the elements in the codomain should be mapped. I never said that. The only requirement here is that all the elements in set X, or domain as we call, should be mapped to one and only one element in Y. So these are called functions. These types of mapping relationships are called functions. So in order to be a function, every element of set X must be matched to a unique element. So every X has a unique element in Y. In other words, no two different Y for same X, same elements. Like this, say you have an element here, you cannot have two different elements like this, right? But this is okay. What is this? You can have two X's mapped to one element in Y. This can happen. So this, in both cases, this can happen, but the previous case cannot happen. Okay, so the definition of function implies every element in X must be mapped to an element in Y. You know that no element X should be mapped to two different elements in Y. This is called uniqueness, right? So you can have only one element in Y, unique element in Y for each X's in the set of X. So elements in Y can have more than one element or more than one element in X. So Y can have more than one element, like this. So one Y can have more than one element, right? Two X's. Y can have two X's. There can be elements in Y that are left out, right? So not all Y's should be mapped. That is what you should know. All the elements in X should be mapped, and one element or an element in X should have only a unique Y, a unique element in set Y. And there can be elements that are left out in Y, so we don't worry about that. Okay, so keep those things in mind and try to figure out what sort of mappings. So we talked about 4 different types of mapping. So out of 4, what relationships can be called as functions? So I have mentioned here function. Can you guess? So this is one-to-one mapping, this one, this is many-to-one mapping. Can you guess which is a function and which are not, which can be called a function and which can't be called a functions? So we can, you can try this out and ask me during the next class, where we'll discuss this and see how many of you have figured it out. So try to do it. Until until next time. Okay, in this case you know that this x, so one element is not mapped to any element in y in both cases. So keep these things, be cautious and try to figure out which of these can be called functions. Okay, so when we talk about functions, algebraic functions, we have to come up with the notation. So you may have seen a part of the notation. So people have different or several types of notations used for a function, so different books can have different notations, but generally they'll be we are using one notations in your scope, in your syllabus. So we'll look into it first and then we'll talk about other types of notations as well. So generally we use symbols f, g, h, anything, right? Anything as you like. So generally we use f, g and h to denote a function generally. For example, told you that so y okay, let's talk about it later. Okay, so x, as you have seen earlier, x denotes an element of the domain. So in general, right, in general you can have different variables for this, like t, s, anything uh, in the alphabet. So y in general, simple y denotes an element of the codomain, right? These two, please remember these things. You have seen that y equals what? Mx plus c. So this is the formula for line, straight line. So here y represents an element in the codomain and x represents an element in the domain, right? So okay, and y is called the image of x under the function f, right? So I told you that what a function do is, here you have a function, let's say for this, for the sake of this argument, not argument, for the sake of this statement, let's call the function as f. You know that you can call it anything, but I'm going to call it f. So what f does is, there'll be inputs, there'll be outputs. So in these notations, uh, the input is symbolized by simple x's and the output is symbolized by simple y. So x is mapped into y. That is what a function do. Okay, so this y here is called the image of x, under the function f. So depending on the function, there'll be different types of y. For examples, let's say y equals 2x, right? And another functions, say call y equals 2x plus 1, right? So we can see that for one input, let's say x, you get two different y's, because these are two different functions, right? We'll talk about functions later. Now this is just to tell you what these are. And so the image is, y is called the image of x under the function f and is denoted by fx. So you may have seen this when you talk about functions. You're generally using this representation, fx equal 3x plus 1. Let's say this. So fx is also equal to y, right? So sometimes use y equals 3x plus 1, or sometimes use f of x is equal to 3x plus 1. So both these things, both notations can be used, so it's up to you. So but we usually use for the simplicity, y equals 3x plus 1, and depending on the type of problems we are solving, we will go between these two representations. Okay, so fx is called the image of a function. Right. Now domain, how do you symbolize the domain? You cannot just write the domain, so instead you have a symbol for this. Domain is represented as d sub f, right? So this is the domain of a function represented by f. Let's say you have a function represented by g, then the domain of the function is written as domain of g, right? Same goes for the range. You know what the range is. Range is the output you get, right? And the codomain is written as cf. Codomains is all the possible outcomes, but rf is the outcome you get under this operation of f. So another thing you should know is that the x in the domain is called the independent variable, right? So what we do usually is we change the input, right? We change the inputs. Even when it comes to cooking, we change the recipe, the input that goes into the recipe. When we change the recipes, we have to change the input as well. Then we get a certain output related to the operation. And y is called the dependent variable, right? So y is dependent. For example, the pizza is dependent on how you arrange the input, right? So x is the independent and y is the dependent variable. These things you have to make sure you know these things, right? So the notation of a functions, this is how we represent the function is function f, right? As I told you earlier, function, what does a function do? A function maps certain x to a certain y, right? X goes into this black box and the function will put it out as y, right? So function f relates an element x in set x to an element y in set y. So this picture is represented by using algebra, like this algebraic notations. How do you represent a function f such that function f such that such that it maps, forget about it, it maps the set y, so set x, right? So here you can see here that the capital X is written typed here and capital Y is typed here. Set x mapped to set y, right? Same thing in the picture as I represented earlier. Y, x, you cannot draw these things in your maths book, so instead you come up with a notation like this, right? The function, certain function such that x mapped into y. So function here is a rule actually, right? It decides how any object in set x is mapped to objects in set y. So function is rule, it governs how it is mapped. It's like a boss. Okay, so and y is f of x, right? So this is the notation function x, set x is mapped to set y. You can also write it as this, y equals f of x. y equals f of x. In simple terms, y is a function of x, right? So as an example, let's take this. A function maps the set of real numbers, this is R, set of real numbers, to a set of real numbers. So this is the domain, this is the domain, and this is the codomain, right? Set of real numbers back to set of real numbers. So what is a function? So when we talk about functions, we are gonna have to define the functions. So this is how you define the function. Say fx equals x plus 1, right? This is how you define a function. This tells you that whenever you input x, the output goes as x plus 1, right? So you have to define the function. You cannot just write this and leave it at that. So in this example, x plus 1, right? So why did I use r into r? So what is this? What is y equals x plus 1? What does this represent? This represents a straight line. So if I draw this in the Cartesian plane, y x plus 1 goes like this, right? What does this mean? Each x has a unique y here, right? Only one y. Take any point, let's say this point has a unique y and unique x, right? So all the x values, so this is a number line, this number line extends to positive infinity this side and negative infinity this side, right? Positive infinity. This one does the same thing. So for every x value there will be a certain y value, right? So all of these y and x values belong in the real number set, right? So any number from the real set can be mapped according to this relationship. So here the domain is R and codomain is R. So what is the range here? The range is all the outcomes from the domain under the operation of f. So in this case, range is equal to the codomain, right? Because all the real numbers will be mapped in this case as well. So this is a simple example. We have to do many examples in order to get used to these function notations and how to define domains and range, how to figure out domains, how to figure out range, how to figure out codomains likewise. Because usually this relationship is given, right? The notation is given, but sometimes you're only given this one, right? You are not given the domain, right, or the range. So in that case you can have to define a domain, or in a cases where you come up with your own functions, you have to define the domain. Domain means all the x values that this function is valid for. Okay, there's another example here. So I think this is the same example we saw earlier. This is another one. Here the set of counting numbers or natural numbers is mapped to natural numbers as well. So what is the function here? Function y is a function of n. So the function, the rule is given by n squared, right? So take any n from counting numbers or natural numbers, take any n element and it is mapped to n squared, right? This is the relationship. You can check whether this is true. Say for example 2 is a counting number or natural number. 2 is mapped to 2 square. What is 2 square? 4, right? In this case 1 is mapped to 1 let's say n equals 1 is mapped to 1, 2 is mapped to 4, right? So let me represent this here like this. 1 is mapped to 1, so this is set n, again set n, and here 2 is mapped to 4. But what happens to 2 and 3 here in the codomain? 2 and 3 will not be mapped, right? So we are talking about counting numbers or natural numbers. So in this case, you know that the values between 1 and 4 according to this relationship are missing, right? So it doesn't matter, we are representing the codomain here, all the possible outcomes. So the domain, all the values in the domain will be mapped. So sometimes we use 0 as well here. 0 will be mapped to 0. Okay, so this is some other notations that we can use. This let's see what this means. Like in the previous case, you saw that this is f, so there will be two dots here. It is such that capital X map to capital Y, capital X map to capital Y. So in this case we represent the set itself, right? But here we use the simple cases, right? This means an element of the domain is mapped to an element of the codomain, right? So when you represent it like this, you have to mention the domain here, right? X is a set of X and codomain Y is a set of Y, right? This is one sort of notation, and another notation would be X, a simple X towards f of X. So what is f of X? You know, f of X is the image, right? We seen earlier, f of X is the image of X under the operation of f. So in this case, so you don't mention the Y here, so you have to only mention the set of X. Okay, so this is an example like that. So f such that X is mapped to, this is f of X, 2x minus 2. So 2x minus 2 is f of X. You can write it as this, f of X equal 2x minus 2. Same thing, right? They say that the domain is set of real numbers, right? So like in the previous example 1, this is a linear map, a linear function. So it gives us the equation of a straight line. So from the theories, you know that for every x there'll be a y, so there'll be unique y. So the range will also be a set of real numbers, right? So here, that's what we have mentioned. The domain of the function will be the set of real numbers, and the range, what is the range? Range will be also the set of real numbers, because all the real numbers will be mapped in this case. So x is a rational number, rational, anything. Okay, this is another example. Look at this is a good one. So x is mapped to the square root of x minus 2. Okay, at the beginning of this video I told you that we are focusing on real numbers, real number sets. We're not focusing on imaginary numbers or negative values of square roots, right? So in this case, you can see that when x is less than 2, what happens to x minus 2? X minus 2 becomes negative value. So what is the square root of a negative value? that is an imaginary number, but it is not a real number. So we have to exclude anything that will give off a negative value for this expression x minus 2, right? So in order to exclude those points, we cannot just leave it as x is a set of R, right? In the early example, when you have a linear form or a straight line, you can leave it as at this. You don't have to write this. X is a set of R. But in this case, you know that you cannot have negative values of the square roots. Therefore, you're going to have to redefine the domain. How you redefine the domain? You have to mention the condition here that x should be greater than or equal to 2, right? So when x is equal to 2, you get 0. What is the square root of 0? Is 0, right? So that is a possible answer. So x value should be greater than or equal to 2. When this is greater than or equal to 2, these expressions become positive. So positive, the x square root of a positive value can be found. It is easy. It is also real number. You may notice that I didn't write here plus or minus, right? So there's a reason for that. Since I did not write this is either plus or minus, which means this is plus. I'm taking the positive square root. So in this case, the domain here. You can write within brackets x is an element of R, comma x is larger than or equal to 2. This is how we write the domain. The set notation. But what about the range, right? So the codomain can have the set R, doesn't matter, but the range is a subset of codomain. Range is the outcome that you get under the operation of f. So here, all the outcome, can you have any negative outcome? No, because we are only taking the positive value of the square root. So this would definitely give you a positive value, right? Positive value. Therefore the range should also be a real number, but I'm sorry, this is wrong. This should be y, right? Sorry, let's it should be y. Y is a real number, but y should be larger than 0, right? So this is a set notation within brackets. You have to write this. Range consists of all the positive real numbers. So you have to mention the condition here. How do you mention the condition for positive real numbers? You have to write y is larger than or equal to 0. In other words, you can write this set as set of real numbers plus here as a superscript sub 0, which means it also contains 0. What happens when x equals 2? When x equal to, this becomes 0, so that gives you 0. So in other words, in another way, you can write the range as this. So square bracket on the left side, 0, comma, infinity, and the parenthesis. Why do you have the parenthesis? Because this is an open interval at the infinity, but you can equal to 0, right? There will be zeros. Okay, what about this? The same examples, but I have changed the sign here. So the domain does not change. Domain is the same as before. I have written here. But what about this, right? So y is also a real number, but now all the y's are negative except when it is 0, right? So it should be 0 less than or equal to 0. Okay, so this is another way of looking at it. R sub 0 super negative. And also we can write it in this form, open parenthesis negative infinity, which means it is not equal to infinity. Infinity is not a number until 0, closed bracket. Closed bracket, which this means you can have this equal to 0. Okay, so when we are as I told you, sometimes they define the domain and the codomain, but in certain cases, especially when you are coming up with the functions, you have to define a domain. So we should learn how to define domains of certain functions. And since we are dealing with real numbers, right, real numbers, the domain can include the set of real numbers or subset of real numbers. What are the subset of real numbers? You can have the set of rational numbers, set of irrational numbers, set of integers. Those are the subsets of real numbers. So important things to remember is that division by zero. What is division by zero? I told you, we have mentioned this earlier. Any number, say a, divide by zero. So you cannot have this, right? So you should remember to exclude any points which gives you a real number divided by zero. Any points. Let's say y equals this. Let's talk about this relation 1 over x, right? If we write x as an element of set of R, this is okay for all the values except at x equals 0. What happens? X equals 0, this becomes 1 over 0. So you cannot have this, right? You cannot have that. So you can have to define the domain such that bracket x is a real number, right? But x cannot equal to 0. So this is the condition. So you write the condition next. So like that, you have to exclude any numbers, any possibilities that can have division by zeros. And what is this? Negative numbers of square roots, right? So let's say you have square root of x, y equals square root of x. So x cannot be negative. So x can be in this case you can write domain as what? As this, plus all the real numbers including 0, right? All the real numbers, all the positive real numbers including 0. So you have to keep these in mind when you're dealing with finding domains and range of the functions. So we'll look at some examples during the class. If you have any questions, please ask me at the next class. Okay, thank you.